In this video we're going to discuss dispersion in a waveguide. Now during the course of Phys 2201 Classical Mechanics you may or may soon be seeing a treatment of dispersion where it is due to the medium in which waves are propagating. In a waveguide, however, dispersion arises because of physical spatial constraints that are put on the wave, and that changes the way it propagates, and that's what we'll talk about in this little video. So first, here's some examples of waveguides. This first example is a microwave waveguide where electromagnetic waves in the microwave frequency will propagate through this rectangular cross-section pipe. This is an optical waveguide where here we have some contrast in the refractive index, and this contains a wave of light that travels along this waveguide here. An optical fiber is an example of a waveguide. The light waves travel along the length of the optical fiber. And a trombone, or indeed any other wind instrument, is an acoustic waveguide where the sound waves propagate through this pipe. So waveguides, basically, they're a pipe and the wave is traveling along the pipe. So what happens to waves in a waveguide? Well, here I'm going to give some spoilers and give you an example of a wave propagating in a waveguide. In this example, it's a 2D waveguide. That is, we have a wave that can propagate along the x direction, but in the y direction we have boundary conditions at the surfaces along here and the other surface along the bottom here that mean the wave cannot propagate in the y direction, rather it's reflected off these boundaries. And we're going to launch a wave that as its initial condition has more amplitude on one side than at the other, so we have a little peak over here. So we launch this wave and we see what happens. And so we get some sort of complicated wave motion, which after a while starts to resolve itself, and we see that the wave is separated into different components. And so if I stop the wave motion now, what we see is in the furthest along the x-axis, so the waves that are propagating the fastest, are these waves that look like plane waves. They are constant in the y direction and they're propagating in the x direction. So they look like plane waves. That's kind of the plane wave solution. Further back we have a different sort of wave where we seem to have, if we took a cross section in the y direction, we have a maximum here and then goes through 0 and then a minimum, and then it oscillates. It looks like a standing wave in the y direction. And in the center of the waveguide we have a node where the amplitude is always 0. If we go further back again, I'll let it propagate a little bit further so we can see more clearly. If we look at the next slowest wave, we come back here, and now we have 1, 2 nodes in this direction. If we took a cross section through here, we'd have a maximum, then minimum, then another maximum. And so kind of what it looks like here is that we have waves propagating in the x direction, but the waves that have different spatial patterns in the y direction propagate at different speeds. And that's a key thing about waveguides, is we have what we call modes, and these modes can travel at different speeds. So in the y direction, the key thing about the waveguide is you have boundary conditions at the walls. And for acoustic waves, the velocity of the wave in the y direction must be 0 at the walls. Now actually I've misspoken a little bit here. What I mean is the velocity of the particles. So we're talking about an acoustic wave. The particles of air, the nitrogen molecules, the oxygen molecules, they must have 0 velocity in the y direction at the walls because they can't travel through the walls. So they must be stationary at the walls. So that's the boundary condition. And this means, as I said before, we have standing wave modes in the y direction because we have this boundary condition that clamps the speed of the wave in the y direction, and that's exactly the kind of thing you get when you have a standing wave. So for example, if you have a string, you clamp the ends of the string and get a standing wave in the string. In the y direction, what we've done is we've put some boundary conditions on that mean the wave in the y direction is a standing wave. And now we're going to do a bunch of math to see how that works. And the final thing is that it does impact transmission of the waves in the x direction because these different modes that have different patterns in the y direction travel at different speeds. And again, the maths will show us how that works. Okay, so we're going to do this for an acoustic wave, a sound wave propagating in a pipe, in a waveguide. And so to start with, we're going to need an equation for a sound wave. So we've got this equation here. This is the three-dimensional wave equation where this grad squared is all the second order spatial derivatives. We'll see that a bit more about that in a minute. And c squared, the square of the velocity, is given by this ratio of gas constants, heat capacities, temperatures, molar mass, and for air it comes out to be about 350 meters per second at standard room temperature and pressure. That's a wave equation. So step 2, we need a boundary condition at the surface, as I've already mentioned. So the boundary condition is that the velocity of the gas perpendicular to the surface is 0. Otherwise it would be going through the surface, and that's not allowed. It's a hard surface. This means the acceleration of the gas perpendicular to the surface is also 0. Force is mass times acceleration, so the force must be 0 perpendicular to the boundary. That is, the force on the gas molecules must be 0, otherwise they'd have some acceleration. Now the force in the gas is given by a difference in pressure. Therefore, the rate of change of pressure perpendicular to the surface is 0. So if we took a derivative of the pressure perpendicular to the surface, we would get 0 at the surface. That's our boundary condition. The derivative of the pressure in the spatial direction perpendicular to the surface must be 0, and we're going to use that to apply the boundary condition later on. Okay, so this is our pipe. We've got propagation in the x direction. We have dimension w and dimension d in the z and y directions, respectively. The force on a gas is given by the difference in pressure. Therefore, the rate of change of pressure perpendicular to the surface is 0. So we'll introduce the geometry of the situation that I've shown here, and the boundary conditions can be written as dp dz is 0 at z equal to 0 and z equal to w, and dp dy is equal to 0 at y equals 0 and y equals d. So what's that saying? For example, in the y dimension, which is this direction here, at 0 and d, the dp dy, that is the derivative of the pressure in this direction along the y-axis, must be 0 at these boundaries. That's our boundary condition. So we start off with the wave equation. Now we expand this grad squared into the second order partial derivatives in space, and this is our full wave equation now. And we're going to assume a solution of this form. That is, the variables are separated. So we have functions of x, y, z, and t that can all be separated and written as separate functions multiplied together like this. If we substitute this solution for p into our wave equation, then we get something that looks like this, where these lowercase double x, double y, double z, and double t indicate the second order derivatives, like this. Now what this means, if we divide through by p, we divide through by the function x times y times z times t, we get this equation here. Now each of these terms must be a constant, because if I change something about x, then this ratio here may change, but we can't then assume that something about y and z and t changes, because these are independent variables. So each of these must be a constant. And this is a standard technique when you're solving these sorts of equations. This is called a separation of variables. So, if each of these terms is a constant, then what we can do is assign a constant value to each of these ratios here. So we assign a value of negative kx squared to this ratio, negative ky squared to this ratio, negative kz squared to this ratio. And we've kind of anticipated what these constants are going to mean as we continue through this working. So we can define also the sum of the squares of these constants as k squared, and therefore we get that the negative kx squared minus negative ky squared minus negative kz squared, which is all of these terms here, must also then be equal to this last term here that depends on time. So this last term here must then equal negative k squared. So the equations in blue, if you look at these equations here, these are equations for simple harmonic motion. The solutions to these equations must be sine or cosine functions, or mixtures of sine and cosine functions. So we have sine and cosine solutions, or complex exponential solutions, to the function x, the function y, the function z, and the function t. So now, having derived these equations of simple harmonic motion, we can use the known solutions. I've written them here in terms of complex exponentials and their conjugates, where the a's are some amplitudes, and we have the kx, y, and z, and the frequency omega, which is equal to k times c, relating this back to the variable here, k times c. Okay, for the y and z components, I'm going to rewrite this solution in terms of cosine and sine functions, because that will make it easier to apply the boundary conditions, which is what we'll do now. So remember, the boundary condition for the z direction was that at z equal to 0 and z equal to w, the derivative in the z direction of this function is equal to 0. So the z function of z is this function here, this cosine and sine function. If we take derivatives in z and then require that derivative to be equal to 0 at these two positions of z, this implies the function z must be a standing wave that has this form here. It must be a cosine function of kz times z, where kz must be equal to integer multiples of pi divided by w. So m is an integer. That's the function for z, and we get a similar sort of function for y with the same sort of treatment. So these boundary conditions force this solution. It forces a mode in the y direction and a mode in the z direction that is a standing wave. So these two functions here are standing waves in the y and z direction. In addition to the standing wave, to get a mode that propagates along the waveguide in the x direction, we can add a travelling wave component to these, and then we have these waves where they have some sort of mode shape in the transverse direction, the y or the z direction, and propagate along the x direction. And that's how we construct these modes of the waveguide. But the basis underlying all of this is that in the y and z directions we have these quantized standing waves. So we have two equations to go, those for x and t. So we've got them here, and we can write the equation for x times t as being equal to all of this. When we multiply it out, it's pretty ugly, and I can uglify it further by writing it like this, and then I can simplify it a bit by writing it like this, where all of th's d's can be written in terms of the a's, ax's and at's. You can go through this, or you can just take my word for it. And taking only the forward propagating waves, that is the waves that are propagating in the positive x direction, that's the ones with the negative sign here, so that we get the forward propagating waves, then this function x times t is this function here, which looks like a cosine wave, omega minus kx times x, with some phase. So the phase in the x direction is somewhat arbitrary. And this is a propagating wave in the x direction. So finally, putting all this together, we get the following. Our function p, which we separated into functions of x, y, z, and t, can be written like this, where a is equal to the product of these amplitudes, ax, ay, az. The k's, ky, and kz are integer multiples of pi on d, pi on w, and k, the total wave vector, k squared, is equal to the sum of the squares of all the k's, and k is equal to omega on c. So let's see what this means for waves travelling in the x direction. So for example, for n equal to m equal to 0, that is, these cosine functions here are equal to 1, then we just have a plane wave travelling down the pipe. There's no dependence on y or z. So when we looked at that example right at the beginning of this little video, we saw that there was a plane wave solution, and that was the fastest wave. That is this wave here. So this is the solution with n equal to m equal to 0. And if we look now at a different solution, if we have n equal to 1 and m equal to 0, then we have a function now that has some dependence in the y direction. Now we have a standing wave in the y direction, and so we see a solution that looks like this, where we have a node down the middle of the waveguide and we have antinodes on the edge. If we look at a cross-section of any point along the x direction, so we take a cross-section at some point in x and take a cross-section through y, we see a standing wave in the y direction. Furthermore, we can also find kx. Since we know k, this k here, which is equal to omega on c, we can find kx, and kx is going to be k squared minus ky squared minus kz squared. In this case, k squared, kz squared is equal to 0, but kx is going to be omega squared on c squared minus pi squared on d squared. So kx is smaller than k. And this is why this mode here must always be slower than the plane wave solution, because some of the k vector has been sucked up and used to give you this standing wave in the y direction. If you have example now where n is equal to 2, you can see kx becomes smaller again because this thing you're subtracting here, this ky term, becomes bigger. We have more nodes here, and the standing wave now becomes a little bit more complicated. If we now add a mode in the z direction as well, so we add m equal to 1, we take a little bit more off this k vector, which means this mode will be even slower again. It looks really pretty though. We have nodes along this plane here along z, and then 2 nodes along here, and this is now a 2-dimensional standing wave that looks like this. So let's now return to these equations and think a bit more about when modes will and won't propagate and what it all means. So the first thing to say is that kx, ky, and kz are wave vectors in the x, y, and z directions respectively. And the vector kx, ky, kz really is the direction of the wave propagating along the pipe. The catch is that because of the boundary conditions, ky and kz must be quantized. That is, the wave in the y direction and the wave in the z direction, to satisfy the boundary conditions, must form a standing wave in these transverse dimensions. Kx, however, that is free to choose in the sense that there is no boundary condition in the x direction. We're going to have wave either propagating along the pipe or a wave not propagating along the pipe. So in the x direction, kx will only be real if this condition is satisfied. So we're looking back up here at the equation for kx. We can turn this overall total k vector into something that depends on the temporal frequency and the speed of the wave. And if this frequency here is too low, then for a given mode where n and m are not 0, then this square root here will become imaginary. So if you want to launch a higher order mode with n or m or both being non-zero, you need to have a high enough frequency to support those modes. For n and m equal to 0, that doesn't matter. You can have as low a frequency as you like. But for modes where n and m are non-zero, you need a particular frequency before those modes are actually allowed. And this condition is not satisfied if omega is not greater than this, then there is no propagation of that mode in the x direction. The dispersion relation in the x direction can now be written as this. So this is a relationship between the temporal frequency omega and k in the x direction. And this equation here will tell us the phase and group velocity of the wave propagating along the pipe. So that's the dispersion relation in the direction along the pipe. Just on this idea of whether modes do or don't propagate, let's look at a particular case. If we inject a frequency omega is pi c on d, what will happen to the mode n equal to 1, m equal to 0? So we calculate what kx is, we substitute in the value for omega and the values for n and m, and we find that kx is exactly equal to 0. So in this case, the wave will be stuck. There is no propagation along the x direction. The wave could travel along the pipe in the 0, 0 mode, that's fine, but it can't travel along the pipe in the n equal to 1, m equal to 0 mode. So the frequency of the wave omega in this case is not quite enough to support a wave that travels along the pipe. It's only just enough to support the standing wave in the y dimension. So if you launch this wave, say if you launch it with a particular pressure profile down this end, you might get a standing wave going backwards and forwards along this pipe, across the pipe rather, but it won't be traveling along the pipe. There's not enough frequency left over to allow a non-zero k. In cases where we have kx squared less than 0, the mode, mode becomes evanescent and decays exponentially along the pipe, and energy in that mode ultimately will be reflected back towards the source. And when kx is greater than 0, the mode will travel along the waveguide, but at a speed lower than the n equal to 0, m equal to 0 mode. We can plot the dispersion relation here, so we can plot omega and kx, and we can do it for different modes, and this is what we see. And the parameters for this plot, if you're interested, are given up here. Now what we see is that the 0, 0 mode, n and m both equal to 0, exists for all frequencies, and it's a straight line. It's exactly the same dispersion you'd have in free space. The higher order modes, however, don't exist until you get to a particular frequency, a frequency that is high enough to support a standing wave in one of the transverse dimensions, and then that mode will switch on. And you can see they have different cutoff frequencies as we go up. And if the driving frequency is below the cutoff frequency, that mode cannot exist. So at this frequency here, the only mode is a 0, 0 mode. At this frequency here, we have 2 modes. At this frequency up here, we have 3 modes. And these are the cutoff frequencies when these modes first appear. Now there's a question as to which modes will actually be launched. So when we launch a wave at the start of the pipe, the shape of the pressure at the beginning of that pipe can be decomposed into a sum of different Fourier components, and that will tell you which modes are launched. So for example, with this particular pressure profile here, which I can play like this, I can write that as a sum of these 3 modes here. And so if I drive the end of the pipe with this pattern here, in fact what I'm doing is I'm driving it with a superposition of these modes. And that's the 0, 0 mode, the 1, 0, and the 2, 0 modes. In this case, where I'm just looking at a single transverse dimension. An interesting thing about this is that these modes have varying spatial frequencies, but the same temporal frequency. So if you're thinking back to the situation where we looked at waves on a string and we looked at different modes, as we increase the spatial frequency, we increase the temporal frequency as well. In this case, the temporal frequency remains identical. We're just driving this waveguide with a single temporal frequency, but the spatial frequency is changing. Nevertheless, we can decompose whatever profile we have here into a sum of these different Fourier components in space. Now we can go back to that movie we first saw at the beginning of this video and reinterpret it, or look at it again, knowing what we know now. So if we look at this before I start the animation, you can see that I've given it a particular pressure profile where the pressure is high on this side and lower on this side. So the redder the color, or the more intense the colors, the higher the pressure variation. So I've given it some sort of pressure profile which is very intense on this side and lower on this side. So we're launching with some combination of different modal shapes. And then that pressure oscillates at the frequency omega, which is the temporal frequency. And then that initial distribution of pressures launches waves with different modes, and these modes split apart as they propagate. The 0, 0 mode goes the fastest, the 0, 1, or the 1, 0 goes the next, then the 2, 0, and beyond that we have higher order modes. At the very base of the system here, there will be other modes that are not propagating. There'll be evanescent waves here that are being reflected back towards the source, because we do not have a high enough temporal frequency to launch all of the modes that are needed to decompose this initial choice of pressure distribution. So, in summary, the initial conditions are broken up into a sum of many modes. Some of them propagate, but they do so at different speeds. Some modes are beyond the cutoff, and these higher order spatial frequencies are not transmitted down the pipe, they're evanescent waves. And you can generalize all of this to other sorts of waveguides. So if you ever heard the term single mode optical fiber, what it means is for a given frequency, that is a given frequency of light, there will only be a single mode allowed in that optical fiber. And if you're doing communications with optical fibers, you really want them to be single mode, otherwise things can get pretty complicated in terms of when the information will arrive at the other end of the optical fiber.